So, welcome back. So it's my pleasure to introduce you the next speaker for this talk before lunch. And it's my pleasure to have here with us Gapsis from Max Planck Institute for Biophysical Chemistry, Germany, Tübingen, right? No, Göttingen, Germany. So, stage is yours. Thank you for coming and for giving the talk.
Thank you for the invitation. The sound all right? All right. Thank you for the introduction again, and I'm sorry that Bert L, who had to give the talk today as well, he couldn't be here unfortunately, but I will try to fill in his shoes and give an introduction into the alchemical free energy methods first, and then I'll follow with some applications that you could also think how to use those applications in your projects potentially, and those will cover a wide range of different systems and different biomolecules to which you could apply potentially these alchemical methods. But in the first part of the talk, I will try to put these alchemical methods into the perspective. So far, as far as I know, in the workshop, you listen more about the bioinformatics or chemoinformatics-based approaches, including docking or ligand-based design of protein-ligand complexes or so. But now we will continue with what Modesto started today. So with the simulations, molecular dynamics-based simulations, and in particular, how to extract free energies from these simulations. Right, so what are those free energies and why do we actually care about them? So the free energies, you could view them also as a synonym to the affinities. Affinities of what? Affinities of protein-protein interaction, affinities of ligand-protein binding or protein-DNA binding. And it is exactly the property, the very much integrated property, property integrating all of the degrees of freedom and all of the interactions in the system that we are after when we are trying to design potentially stronger binders of different biomolecules. Another way to see where these free energies could become useful is looking at the stabilities of proteins, for example. We may want to engineer a more stable protein than the wild type that exists in nature, right? So we would like to mutate that protein, but in a certain way, right? In such a way that its folded state would be more stable than its unfolded state in comparison to the wild type. And this is exactly the free energy difference that we are after. So we want to lower the free energy of this mutant protein. Also, the rates can be viewed as how they are related to the free energies. They can be viewed as the height of the barrier that the transition needs to cross from one state to another, right? The higher the barrier, the slower the rate of this transition would be. BImBS, that also what Modesto was showing, they're also integrated properties of so potential of mean force. That is also just a free energy landscape. So we are in very many situations we're indeed interested in capturing the free energies or their differences between the different states, different variants of the molecules. And alchemical free energies will be just one flavor how to extract these differences from simulations. There are, as I mentioned, there are many methods, and that also highlights the importance of the free energy as a concept. There are many methods that try to capture them, and what we will be looking at today is the first principles based approaches. So first principles means that they're based on the first principles of statistical mechanics and underlying sampling method for this is that I will be showing will be always molecular dynamic simulations, but you could also imagine a Monte Carlo based sampling or so, but all of them will be relying on the extracting free energy based on the first principles of statistical mechanics. There are also, on the other branch, I would call them statistical methods. These statistical methods would be much more in line with what you heard in the first part of the workshop, so bioinformatics and chemoinformatics-based approaches. So, for example, ligand-based design would be a classical application of a chemoinformatics approach, while what I mean structure-based ligand design is docking, and all of these docking approaches could be categorized there. There are also hybrid methods that are somewhere in between. They're using some features from the first principles-based approaches, for example, running some simulation and later using descriptors from those simulations in one of the statistical approaches, right? So combining both. But we will go the branch, this branch now. And there are various ways, we'll cover them now, how to extract free energies. The most intuitive would be Boltzmann counting, so simply run a simple simulation and count how frequently the system is in one state, how frequently it is in another, and we'll see how to connect them to free energy. But there are also, at the biggest branches, probably of all the zoo of methods, they are all biased sampling. So you could enhance the sampling by means of umbrella sampling, conformational flooding, metadynamics, or you could use alchemical methods. It's another way of biasing your simulation. And there are also several branches of those, and we'll cover those in the introduction further. All right, so let's have a look at those methods. And also, let's look at what this free energy is and how differently it can be expressed. So from the thermodynamics perspective, one can express it with this equation. It's very well known probably to everyone because it is one of the, we probably covered in most of the courses, whether you are a pharmaceutical science student or a physicist, but you will know that it is free energy is the difference between the enthalpy and the entropy, right? And entropy here has also a component of temperature there. So we could have this thermodynamic description. We could also write it down as a logarithm of the partition function. So it's statistical mechanics interpretation, where partition function is integration over all the degrees of freedom of moment and coordinates of the system, and the free energy will be, the absolute free energy will be just logarithm of that huge integral. Also, here it is another expression where we can directly relate now. This should be a proportionality constant, probably better, but nevertheless, it is free energy is proportional with this Boltzmann weighted. Free energy is proportional to the probability. That's exactly the point that I was trying to make with the counting. So this would be, for example, exactly how simple counting would work. We would count the system in one state, in a system in another state, and their ratio of their probabilities related would be related to the free energy difference between them. That would be the counting. Also, we could express the force acting on a particle as a gradient of the free energy, and we could also exploit that relation, for example, in biasing, in force bias simulations, trying to obtain the differences between the wells and the free energy. And there are many approaches, as I mentioned, that will be using those. So counting, perturbation, and integration, these are alchemical free energy calculation methods, umbrella sampling, metadynamics, non-equilibrium methods. They also can be combined with either alchemical or non-alchemical approaches. So let me again just illustrate how we can view the free energy and how, for example, we could extract free energy difference between two states. So here I'm using an example from an old publication, but it's very nice to illustrate how one can obtain free energy differences by counting. We are looking at the peptide. It's a small peptide, I don't remember, maybe 6 residues or so. So being so small, it has a well-defined folded state, at least at room temperature. If we were to simulate, you can imagine that this is a trace, a simulation trace, and we are monitoring the distance from its folded state, right? RMSD is root mean square deviation from its folded state. And it usually stays in its folded state. Only sometimes it makes an excursion to another state, which we could call arbitrarily, could draw a threshold here, calling it unfolded. So if it is unfolding sometimes at room temperature, it returns. We can simply count how frequently it is here, how frequently it is there, and by means of this previously shown relation, we can extract the free energy difference between those two states. And this is at room temperature. What happens at the, in a warmer room? Well, we start seeing many more discourses from that state, right? So this state is still, we call it folded, but much more frequently it is going away from it. It's not folded anymore because if we look now at the previous equation, at this thermodynamic expression, we are starting to get the temperature component increasing temperature. We're starting this entropy component to start dominating over the enthalpy, right? And this is very nicely illustrated also in this plot. Here, every snapshot is exactly the same system. Simply every conformation now is 1 point. So we can map it into this space and see that there are, so maybe this is the deepest minimum. This is what would be the folded state. But there are also other states that are not, we call them unfolded, let's say, but they are always also populated. But let's just have a look maybe. Yeah, exactly. We have a conformational coordinate, which we could define to simplify the picture. And we can have a look now at those three wells. At room temperature, we had all these three wells populated, but one was the deepest, and it's expressed by the free energy on the y-axis, right? The lower the well, the lower free energy, the more populated it is. What happens now if we color all of these populations by temperature? So at the room temperature, we have those wells, two deepest wells, always folded system, right? And once we raise the temperature, we see those discourses from the folded state into the unfolded states. We basically lift the system up in the free energy, and we do not, and we basically start crossing this barrier. So it's a very intuitive approach how to view the interaction between enthalpy and entropy and describe the free energy, right? So this would be just simply counting and thermodynamic interpretation of the free energies, and it worked because we could always cross this barrier, either by, even at the room temperature, right? We could sample both states, so we could get the free energy difference between them. But sometimes what happens if we do not cross the barrier? So we are stuck in one free energy minimum, and we don't even see another minimum. So we cannot say anything meaningful about the free energy difference because we never cross the barrier to visit another minimum. Well, there are different techniques to approach this. One of them, one of the classical approaches is umbrella sampling. What do we do then? So we actually, this is just the depiction of this problem that I was discussing. We are here, we have a barrier, we would like to know the free energy difference, but how do we cross it and how do we estimate how high this barrier is? Well, we start putting so-called umbrellas. Umbrella is just a term for a harmonic potential, which would restrict the system. Here I'm showing, this is a very abstract picture, but here is a real world example. We may want to know what's the barrier for a water molecule to cross from one side of a channel to another, or for example, from one side of a quaporine or carbon nanotube to another side, right? If water doesn't want to cross through it because there is such a barrier, we start restraining it. So we put water in one position, put a restraining potential, and force water to stay there. It will, if we now histogram all the coordinates and histogram the probability for water to be there, it will be, in principle, it will have a component of the free energy, so how frequently it wants to be there, but it will be biased. The good thing is that we exactly know how much biased it will be. It will be biased by exactly this potential that we put in there. And we can unbias it. So just subtract all the probability for it to be there due to the potential. And then we can recover this nice, basically free energy landscape for crossing this. this, for example, carbon nanotube. All right, so this would be, so far I haven't mentioned the word alchemy in none of these methods, but now here it comes. Is there another, I would formulate the question in the following way. Is there another way to cross a barrier? So again, we have a barrier, and this barrier is related to ligand binding to a protein. We have a protein, this Pac-Man, and a slice of pizza here, and we would like to know what is the free energy difference between this state and the Pac-Man now with a rectangle there. In principle, we would need to sample over the barrier, and tomorrow you'll hear more about these methods. There will be metadynamics approaches, and well, we just looked at umbrella sampling, that's one approach, but could we do this without going over the barrier? And the answer is yes, we could. We could use some alchemical coordinate. And alchemical, of course, sounds a little bit unscientific, but in this case, it's just a computational trick. We would, for the alchemical approach, we would like to actually disappear this slice of pizza here and appear at the same time from the gas phase, we would appear this rectangle. If we were to take all the interactions into account properly, we would get the free energy difference required to do this transformation. And there is theory to do that. The theory goes, one of the approaches, I'll cover several of them, goes as follows. So here's a reformulation of the same problem. We have now, not a rectangle, but this circle here, or ellipse here, being transformed into the slice of pizza. And the alchemical coordinate, so alchemical is because it is not realistic. In real life, we would have here ligand 1 and ligand 2, or maybe we would have here 2 amino acids. One is alanine and another is phenylalanine. How do we transform one into another? Well, we define a coordinate which will actually, along which, this is the so-called lambda coordinate, the Hamiltonian, so the description of the energy, full energy of the system will be transformed from one into another, and at the intermediate steps, it will be a mixed Hamiltonian. So it will be a little bit of alanine and a little bit of phenylalanine. Now, if we drag along this coordinate, so we take alanine and we drag it into phenylalanine, so we slowly transform it, and monitor this quantity. So we monitor the change in the Hamiltonian with respect to this alchemical coordinate. So yeah, just a derivative of Hamiltonian, and use this average over every step. In principle, it should be over the whole ensemble at every step. If we integrate over all of this, we actually end up calculating the free energy difference required. And why is that? It's actually quite intuitive if you view this as simply a force acting on a particle. So derivative of a Hamiltonian with respect to a coordinate is a force. If we have a force and integrate it, we do get work. So if we do it infinitely slowly, the work is exactly the free energy difference. There is no dissipated work. So then we end up at the free energy difference. And this approach is actually, it's known as thermodynamic integration, and it has been described many years ago. It's coming from 1930s by Kirkwood, so way beyond before the actual simulations were started, even before the computers were invented. But the theory is already from those times. And here it's actually an interesting question. Yeah, here it's listed. We are talking now about the free energies, right? So free energy. We know from one of the formulas that free energy has two components, enthalpy and entropy, right? And it's a frequent question. So do we have entropy here? We are integrating only the change in Hamiltonian. So this is just our enthalpy contributions. But we are somehow arriving at the free energies. So actually, did we miss the entropy? We sometimes have these discussions, and even today at the coffee break, we were discussing, is there entropy or is there not? So maybe that's a question to the audience as well. Anyone? Do we have entropy? Or do we need to include it additionally?
So guys, what do you think? Come on, just try, make a guess about your physics knowledge.
Who is for, yes, we have entropy? All right, and all the rest think we don't?
Don't know.
Undecided. No, we don't have.
No,
All right, so the answer is actually yes. Yes, we do have entropy. And entropy comes from the fact that we have these brackets, right? So we do average over an ensemble. It's not a single static structure of which interactions we just look at. Yes, we do look at all of the interactions, but we have to average over the whole ensemble, which is generated at a given temperature. So we are running molecular dynamic simulations, or maybe we are sampling by means of Monte Carlo sampler at a given temperature. So our ensemble, and this is a way to define an ensemble average, it is actually a proper thermodynamic ensemble, which does have entropy, and as we looked at the peptide unfolding at different temperatures, it will have different entropy, right? And or contribution of the entropy, and it would be at different temperatures. This term would be different indeed. So we do have entropy always with the molecular dynamic simulations or Monte Carlo sampling. Right. This was one of the classical approaches, thermodynamic integration. Now it's not the only one, and its competitor or another frequently used approach is free energy perturbation. So here we do not, we again have the same scheme of alchemical coordinate. We still want to transform ellipse into a pizza slice, but this time we do not drag along the alchemical coordinate. We simply simulate or obtain an ensemble of ellipse. So we just gathered many snapshots from a simulation, and we evaluate its energy. So total Hamiltonian. So we just, for every snapshot, we ask what is the energy. And then, without any dragging along the lambda coordinate, we simply take every of those snapshots, and so this is R, right? All the coordinates of those, and evaluate them with a Hamiltonian of B, of a pizza slice. So what would be the energy, what the energy would be if we were to put coordinates of the ellipse into the energetic representation of the pizza slice. Well, it gives us some number which we need to Boltzmann weight and average over the ensemble of all of the conformations that were generated here, and it gives us the free energy difference. Also, we can do it the same way if we generate the ensemble of state B and evaluate with state A. It would give us the same free energy difference with a different sign, right? Inverted sign. And this works very well if we have a good overlap between, if this ellipse is actually very similar to the pizza slice. So these two circles here in this representation, if they're very similar. Because once they are not similar any longer, we start getting huge terms here, and its exponent to the huge term will give us very slowly converging terms in the free energy. These are not unusual things that we have low phase space, a so-called phase space overlap. Well, we can start adding intermediate steps, basically chaining those two circles here with the intermediate gray circles, right? We simply calculate in between of those two, in between of those two, in between of those two. But of course, this means we need to run many simulations. We need then to run the simulations for all of these. And these two approaches, they have their pros and cons. So there is in FEP, in this free energy perturbation, we do have this exponential averaging, while in the TI, thermodynamic integration, we do not. But TI relies on it has this Hamiltonian lag, and it relies on the smoothness of the curve as well. If we don't have this, if this dragging along the coordinate drives the system out of equilibrium, the TI will not give us accurate answer. So it will not be an equilibrium free energy any longer. It will be work which has a component of free energy. And right, so it's often a debate which method is more useful, is more useful maybe in the particular application. But in principle, they work. They both work, and they both give the same free energy. Right. At this point, I will. There are a few more concepts that I need to introduce before going into the applications, and one of them is thermodynamic cycles. We will see quite a few of them in the applications, because it's a very convenient way to summarize what we actually are after by calculating free energies. So here's a typical representation. We are interested in calculating the free energy difference for ligand 1 binding to the protein with respect to ligand 2 binding to the protein. This way we will evaluate how much one ligand is, what's the affinity of one ligand with respect to another. So how one is stronger binder or weaker binder than another. But these calculations, of course, are computationally intensive or require other approaches to enhance the sampling, because ligand needs to sample a large phase space before binding and find also the correct binding pose. But we can circumvent this by going in the vertical arrows. These are exactly the alchemical arrows, right? We need to morph one ligand into another when it's bound to the protein, in another case when it is free in solution. And this would yield exactly the same free energy difference as the horizontal arrows. So double free energy difference, right? Delta G, because we're subtracting two deltas. And this holds because free energy is a state variable and the cycle has to close to 0. So it is all consistent in terms of thermodynamics. It's just that we have those two alchemical arrows. But now, as we learned, there are methods to deal with them. So with the alchemical transition, so we should not worry too much about the alchemical part. All right, what other cycles could look like? So here before we looked at ligand binding, but these cycles can be reformulated to any problem that you are trying to address, or to many problems. For example, we could look at protein stability. So in this case, we would be interested in probing the folding of a protein. So let's say we have an unfolded version of it and a folded version. So we would need to simulate folding of a protein, which is accessible for very small proteins. However, it's very computationally expensive. And for larger proteins, it's not possible. And we would like to avoid this folding transition in the mutant and in the wild type. So we can simply do the mutation from the wild type to the mutant in its folded state and its unfolded state. And the free energy difference will be, again, equivalent as if we were to do the actual folding. And now I was talking always about the equilibrium property, free energy, and I will still remain at the equilibrium description of it, but we will use a non-equilibrium approach to extract the free energies. So this is yet another peculiar application, and we will, today in the practical, we will also use the non-equilibrium approach and look how it compares to the equilibrium approach. It is quite interesting, so I'll spend a few minutes on that. It relies again on the expression of that you already saw. This is the thermodynamic integration expression, and I mentioned that we need to do the transition dragging on this alchemical coordinate along this alchemical coordinate very slowly, so that we're always in the quasi-equilibrium state. Now, what happens if we drop this assumption of the equilibrium, right? Then we end up not with the free energy here, but with work. So we now going from alanine to phenylalanine. We were going very fast. We dissipated a lot of work. We ended up with obtaining this work value. But now there is 20 years ago, Crookes fluctuation theorem was derived. Crookes fluctuation theorem allows us to connect two distributions of transitions of work distribution of going forward. So I'll describe in a second how we obtain those, and work distribution of going backwards to the free energy, right? So yes, these are interesting terms. So how do we get those? We get them in the following way. So we generate two ensembles of structures from molecular dynamics simulations in equilibrium. Wild type, so let's say this is our protein with alanine, and mutant, this is our protein with phenylalanine. And then from the snapshots, we start many non-equilibrium transitions, very rapid ones, and each of those drags the system from its alanine state to phenylalanine state. In each of those, we record a work value. We do this many, many times and collect all the work values in a histogram. So each work value just ends up here as a column, well collected in a column on the x-axis. We do exactly the same in the reverse. So we simulate in phenylalanine and we drag the protein back to its wild type state. We also collect those values. We get two distributions, and here, that's where exactly we come back to the Crookes fluctuation theorem. We actually end up at this expression. We have two distributions of work. Their intersection will be exactly where the dissipation is 0. If the dissipated work is 0, then our work value is free energy difference. So we obtain the free energy difference from the non-equilibrium processes. And free energy is the equilibrium, is the property of a system at equilibrium. That's actually quite fascinating. And today, we'll also use this at the tutorial. And these will be the typical plots that you could generate during the practical. It is exactly running the system in one state, running the system in another state, and these are all work values that you would generate, histogram them, and the intersection will be exactly what we are aiming at. Right, so before I go into the applications, more deeper into the applications, I will give just a small teaser how we could apply. So I have many applications prepared for the second part of my talk, but just very briefly, where we could apply these alchemical approaches. So for that, we could look into ubiquitin, and ubiquitin is a known very promiscuous binder. It binds to it has very multiple binding partners, so it's interesting to probe whether we could control its binding affinity and regulate its binding affinity to certain partners while inhibiting to the others, right? This is the structure of ubiquitin, and it's known to have a very flexible loop. I think I have, there could be a movie, but the movie currently is not running, so forgive me. But the idea is that ubiquitin, this loop in the protein is moving like a pincer. So it can pick on proteins like one would pick with a pincer on a small object, and bind tighter to those to which it needs to be bindings to smaller targets, but it also can bind to very, very different targets with this wider loop opening. If we just simplify this representation of the loop, it's just shown the representation along some reaction coordinate. There are some complexes where ubiquitin is bound to one complex stronger. So the blue is where ubiquitin is bound to a stronger to one complex. Sometimes it's bound to another complex stronger, so switches into another state. Sometimes it's binding to both with both conformers to a partner. Now, schematically, let me just show schematically what is meant by this protein engineering challenge. So native ubiquitin would have two states, right? It could be closed, so pins are closed, and pins are open. And it could make a complex with its binding partner, which would be like this Pac-Man or the, well, let's call it chicken head. Right? It could make one complex or another. But what we would like to try in this test, we would like to try to eliminate one of the pathways that ubiquitin could bind. So we would like to mutate the wild-type ubiquitin in such a way that it would have only this open mouth Pac-Man available. This way, we would eliminate all this pathway, and it could not form a complex with these partners. Only these partners would be available. So could we do that? And indeed, we could. By means of alchemical free energies, we could simply choose to scan many, and think those were hundreds or almost 170 mutations, 70 mutations that were selected not to interfere with actual binding, but only to potentially in the core of the protein to control its conformational change. And alchemically, we can do this quite easily. So we can perform a very large scan, and we can find those that are stabilizing the protein we can construct a thermodynamic cycle such that we're looking at the closed ubiquitin versus open, and some of them, these dots are just mutations, and negative values for the closed mean that the protein is more closed here, and in this case, positive values mean that the protein would be stabilized in more open state. Many of them don't do anything, or it's just within the thermal fluctuation, at the thermal fluctuation level, but there are some mutations indeed that could stabilize the open or closed ubiquitin. We could also then look at another technique. So we discussed umbrella sampling, and we chose some of those proteins to probe in the umbrella sampling regime. And indeed, some of them the green ones are stabilizing the open state, those that we predicted to be stabilizing the open state, some of them really stabilize the closed state. Not always it was so significant, but in this large-scale scan, it was really a big improvement of those from simply randomly guessing or so. It gave us very good leads where to look further. And now we chose several of those proteins to look into closer, and actually to bind them to the partner. So far, we just investigated ubiquitin, which was not binding to the partner. We're looking at two conformations of a protein. But now, if we look at the ubiquitin to binding to many complexes, we can see the following. We had some mutants that were compatible with the complex. So if it's binding well, the mutant would bind also well. And here we don't see any difference from the 0. The biggest change here we could expect to see is just probably given the equally populated conformers in the free ubiquitin would be KT-ln2, so less than a KT. So it's within thermal noise, and that's expected. Now, some mutants should not, in our prediction, should not affect any the complex formation. And again, it's very similar to that panel. But there, where we want to see incompatibility between the mutant, ubiquitin mutant, and the complex, then we see a signal, right? And this signal was further confirmed by the experimental measurements. For these mutants, we would not expect the difference, and for these mutants, we would expect a strong destabilization of binding. And this is exactly what we see. So it's all not. This all was not just a simple computational exercise, but it actually predicted the reality that the conformational shift in protein as expected. All right, so this was just a small example of how we could do this, where we could apply the alchemical calculations, but I have now, I think, exit this. I have a few more examples, and on those I will illustrate also a little bit of the technicalities of how we actually do those free energy calculations and what you would need to know maybe to carry those out in your lab. So we'll look at a little bit at the amino acid mutations, nucleotide mutations, ligand modifications, and before we go further, should we have a break now, or should we not? How much time do we? When do we want to stop?
Whenever you want. The plan of stop is 20
And maybe we can vote again. Who is for the break or who is against? For break? 1 and no break? 2? Wait, I'll ask the question. No break? Quite a few hands. And yes break?
If democracy counts. No break.
If
you want to stop, just take a rest.
For me, it's fine. I'm wondering if you are having hard time now to follow because I now gave a lot of information. Then maybe we can have a 5-minute break.
Yeah. Yes. Let's do like that. Let's do 3 minutes of break. Okay. It's 3 minutes to 12, so we have 3 minutes to break, and then we start. You did a great job.
All right. So I hope everyone is back from the break. Let's continue. So now this part will be far less theoretical. It will be a little bit reflecting on the technical details, how we actually do those alchemical calculations, and highlight our applications to those of those methods. So let's start with the amino acid mutations. Now, here's immediately the introduction of a cycle, of a thermodynamic cycle. But let's have a look at yet another representation of a cycle. But I already introduced it, so it's just a recap of the previous slide. We are interested, firstly, in this first application, we'll be interested in calculating the change in protein stability. So how does the free energy of protein folding, change upon a mutation? So we'll mutate one amino acid into another, and we'll evaluate the folding free energy difference. Now, how we do this? So, of course, these alchemical calculations, they are not standard calculations that you would run, not standard molecular dynamic simulations. You need to do something, right, to the system. So it cannot be just the same, cannot be using exactly the same machinery. And the difference that needs to be introduced into the system is actually the instruction or the knowledge for the system how to transform one amino acid into another. So let's say we have valine in one state. I was using another example, but let's say we're using valine and we want to transform it into phenylalanine. So the system needs to know somehow that in between the two steps, we'll have some mixed states, so this hybrid structure and hybrid topology, valine to phenylalanine, and we have our own toolkit to do that, BImBS. So this is a software package that we will also be using in the tutorial. And this BImBS has the mutation library. It has meaning it has all the rules how to build such hybrid structures. And the rules is just I try to visualize by a bunch of text, right? So all the rules already pre-built. And then it can do it on the fly very quickly, generate you input and which you can later use in the simulation package. And simulation packages, we are using Gromox for that. This is just a scheme. You do not need to go through it. It's just to visualize that we sometimes call to generate all this input, we are calling our library, so PMX, and interfacing it with GMX, so with Gromox, right? So Gromox is a molecular dynamic simulation engine with which PMX is compatible, and that's what we'll be using in the tutorial today. You can also use our web server to generate the inputs. This is this of course makes your life easier. All that workflow can be hidden in one or a few clicks of the button. Right, and what I mentioned, we'll be using in all of these examples that I will show, we'll be using this approach, this non-equilibrium approach, where it would work also with the equilibrium approach. It's simply that due to several reasons, due to several advantages, I would say, we are usually relying in the lab on the non-equilibrium approach. So once again, every time we'll be running 2 simulations of the wild type, let it be protein or the wild type ligand, and mutant protein or mutant ligand. We'll gather the snapshots and make very rapid transitions from one state to another, and from another state backwards, we'll collect the work values and get the free energy difference from those. So this we covered already in the theory. Let's apply this method to protein thermostability. We'll took one of the model systems. It's Barnase. It's a very stable and very well studied protein. You see, it has been mutated, and we also mutated it through and through. Almost every position of it is colored in red. This means that we tried mutating it there to different amino acids. And what it allows us to do is actually quite interesting, right? Now we can, if we can run such a large scale scan of mutations, we can start evaluating protein force fields based on the thermodynamic property. So there is a variety of force fields, as Modesto already presented in the talk before, that some of them will be performing better, some of them worse, and they are all parameterized on somewhat on different sets of data. Some of them are using experimental data, others are not. Some of them are relying more on the QM data, And this evaluation is actually something very orthogonal to how the protein force fields have been parameterized, right? We are really looking at very much integrated properties, so free energy difference of how much the free energy difference of protein folding changes. And we can look at, I'll be showing a few of those plots, so I'll explain. This is average unsigned error, so error from the experiment that our calculation makes on from difference between our calculation and experiment in terms of free energies. And it's averaged over all of these hundreds of mutations or so that we scan the whole protein. And if the value is low, so perfect prediction would be 0, right? We would make 0 error. If the value is high, then we are having a large error, and this force field would be maybe not so good. And for example, OPLS force field is not so good. In this particular example, at least, we have several amber and charm families. Those who are more in the simulation business, you know probably those names. They are doing better than others. We can also do a trick. We can start combining results from different force fields just by training some machine learning algorithm, or maybe just averaging. In fact, just averaging results from two force fields in a consensus way, it gives us lower error than any individual force field. So if you have, the message from this is that if you have a chance to run a simulation in two force fields, do it, and the result will be more accurate than the single force field, even if you run it single force field but longer, right? So it's always advised to do this consensus. But it depends also a little bit on the force fields. If you combine the very bad force field, so OPLS, into the mixture, it doesn't help. But this holds for amber and charm families quite well. We have probed it with another protein, fewer mutations here, but again, the result was very similar, that consensus is doing better than the single force field. And this will be a recurring message in all of the applications that I will show. So this was for protein stability, so difference in folding free energy, but we can also apply it to a different question, in this case, drug-resistant mutations. We could ask the following question. Let's use a HIV protease as an example. What would be the free energy difference, or if we were to mutate one residue or another, but free energy difference on ligand binding? HIV protease is actually such a notorious case which is necessary for the life cycle of HIV. However, of course, people have found drugs that bind to HIV protease and inhibit it. So then, in principle, yeah, problem solved, cured. No, actually, no, it's not the case, because HIV protease does exactly what I mentioned. It mutates several key residues, and ligands, so drugs stop binding to it. It becomes drug resistant, and it can still function as previously. So it would be very interesting to be able to predict free energy differences of the drug resistance upon these mutations. So we need to construct simply a different thermodynamic cycle in this case. In this case, we want to mutate once HIV protease, which is in apo form, so without the ligand bound, and once when the ligand is there. In this way, delta delta G will tell us how much the free energy of ligand binding changes upon the mutation. And we did this for all the known, for the most commonly used drugs that are actually used against HIV, so they bind here, and for most known HIV protease resistance mutations. Yeah, they're just colored there in color. And we get a very good agreement. So basically, we have very good predictive power. This is just our calculation, or experiment versus our calculation. So we have very good trend for this. Absolute values are slightly off, but we basically are able to predict very accurately whether the mutation would be drug resistant. And next, my colleague Matteo Aldeghi, he took it again one or a few steps further. He actually probed many systems, more than 100 mutations with many different, very diverse ligands. He probed for the drug resistance, right? So in a similar fashion as was shown for HIV protease. And we again have a very good agreement with the experiment. The agreement, I'm again just showing quickly these results. It reaches root mean square error, or it's a similar to measure to average unsigned error from between our calculation and experiment. It's about 1 kilocalorie per mole. So we can reach accuracies in predicting drug-resistant mutations up to 1 kilocalorie per mole of making an error of 1 kilocalorie per mole on average. All right, so this was drug resistance, but we can also probe changes in free energy upon protein-protein binding. Where is it interesting? It's, in particular, it's interesting for the antibody or T-cell receptor design. I'm showing an example here of the T-cell receptor interacting with the peptide MHC complex. And the peptide MHC complex is this structure which actually lives on the cell surface, and its purpose is to take small fractions of the peptides and deliver them to the surface of the cell. Next, the next layer, the T-cell receptor, comes to the surface of comes to the cell surface, binds to this complex, and identifies whether this peptide is coming from a harmful, is somehow harmful to the cell or not. And if the cell is marked as harmful, then it's destroyed, right? So it's a fancy security system. But actually, these are just abstract words. How does it bind and how does it identify? There must be some physical underlying mechanism behind that. And this is, of course, again, brings us to free energies, right? That's free energies govern the affinities and binding affinities. So it is the free energy difference that will, in the end, determine whether T-cell receptor binds to this peptide or not, to this whole complex, actually. And people also look into this experimentally. We took one study where a number of mutants were introduced to see how strongly they bind to this peptide MHC complex, and we scanned all of those mutants as well in our computational scan, and we are able to identify them with very high accuracy. Only basically 3 outliers here outside of this acceptable region. We basically now can predict which of the mutations will increase or decrease binding between these 2 complexes. Right, so this was all protein mutations, but we can do also DNA mutations. We can do, we have a module of our BImBS-based setup to do nucleotide mutations. In a very similar analogy, as I was showing the protein library that we can mutate one amino acid to another, we can do one nucleotide into another. It's exactly the same machinery, just replace the building blocks. And the building blocks, yeah, I just mentioned the nucleotides. The library is a little bit smaller, but no essential differences between the 2 approaches. Again, we have a simplified approach via the web server, but everything else is pretty much analogous. All right, now what application we used it for? We used it for protein DNA binding. The thermodynamic cycle is the following, that we are interested in mutating DNA this time, right? Nucleotide, base pair, 2 nucleotides at the same time when DNA is free in solution, and compare it to the same mutation when DNA is bound to a protein. And this delta delta G will tell us how much the free energy changes upon a free energy of protein DNA interaction changes upon a mutation of DNA this time. We probed it in almost 400 mutations over a very diverse set of systems, so including transcription factors, endonucleases, and what know I. Yeah, many of those. And here's immediately going to the results. So we have, again, I'm showing the same average unsigned error, so the smaller number, the better. This is the very much averaged property of the quality and correlation between the experiment and calculation. We can immediately see that there is quite a spread of the values, and the quality that we get is somewhere around 6 kilojoules per mole, which is 1.5 kilocalories. So the quality is slightly lower slightly lower than for the protein amino acid mutations, but the trends are very, very similar. If we are using here amber force field with the one, exactly the one that Modesto was presenting before, so BSC1, with the BSC1 corrections for DNA, we get slightly worse result, and exactly the same result as if we were to use Charm36M, but the combination of both of those gives us a more accurate answer, and both in the trends and in the absolute errors. But this, the plot here, just one word on the plot, is actually quite interesting. Here on x-axis, I'm plotting, so these are all the free energies that we calculated, those 400. On the x-axis is experimental free energy difference. On the y-axis is our calculation. Just by looking by eye here, we see that there are, as if there is a very narrow range where the values are, as if they are cut, right, tunneled there. And it's a little bit speculative, but I would claim that there are some this more or less marks the experimental range in which the free energy difference could be detected, because these are very high values. So basically, that's where binding could be, changes in the binding free energy could be detected. Further, it simply could not register, or would register that it's not binding any longer upon this nucleotide mutation. But of course, for the computation, it doesn't hold. We calculate whatever we calculate in these senses. So this could also be perturbing our, disturbing our accuracies a bit. But all right, what we can do with those free energies further, we can actually start calculating the protein DNA binding profiles. That's quite interesting. This is a typical profile that one could see obtained experimentally. Experimentally, it's possible to do some randomized nucleotide binding assays or SELEX experiments on protein binding microarrays and obtain such matrices where for every position of DNA, one obtains the frequency of a certain nucleotide binding to that position. And this is then obtained from the experiment. But now we have our free energies calculated for all of the sequence. This way we can also calculate the binding profile back from, because free energies are just, in other words, they're probabilities, right? Probabilities of finding nucleotide in a certain position. And this is a result. This is first is our calculation. And those are different experiments for the same system. So the bottom line here is that, at least for me, it's very difficult to distinguish this profile from some of those profiles, right? The difference between the experiments is as large as the difference from the calculation. So we are basically, even for the profiles, we are capturing the pattern as accurately as experiments can capture this pattern. All right, and now we come to maybe the most interesting part, or maybe the most sought after by the pharmaceutical industry, is ligand modifications. And this is also arguably the most challenging part, because for the ligand modifications, yes, we do have module in our PMX setup, but it is not the same as the previous ones. We cannot pre-compute libraries any longer to do the alchemical calculations. Why? Well, because ligands, the ligands do not have the finite chemical space as before. We had before 20 amino acids. We could learn what is the set of rules to make each combination. So every mutation to every mutation, or 4 nucleotides, every nucleotide to another nucleotide. Now we have something very diverse, as I tried to illustrate here. Anything, right? Now the same game will not work. But we can define a workflow, how we could do this. We could, and the workflow, very briefly, I'll go over it, starts as follows. First, we need to identify those atoms that we need to map one to another for the alchemical perturbation. To map the atoms, we are using either ligand alignment and then relying on the coordinates, or using maximum common substructure from the, those of you with a chemoinformatics background, you are familiar probably with these algorithms. Now we tie them into some sophisticated scheme that it has many side branches, and we do not need to go into the details of these, right? It's just to illustrate that we actually rely on these two approaches to get optimal atom mapping for alchemical transformation. So if we have one ligand and another ligand, we can identify how to morph one into another. For example, if we have two such structures, our algorithm will go in different ways and ask different questions, and try to answer them properly. And we'll identify that, for example, the blue one is similar to the gray by allowing those perturbations. Or another way is this, and it will also try to produce an outcome which will run in the simulation properly. Run means that it will not crash and will give meaningful answer. It will build all the topologies and structures automatically. And it can also suggest ligand pairs to map. Ligand pairs, what I mean by that, I'll show also in an example, but here's a brief illustration. Let's say we have a question, we have a small set of compounds that we want to explore. So what do we do? How do we start with it? Do we mutate number 1 to number 2 or number 1 to number 3? Well, the algorithm, we have a way to compute distances between all of them in a given metric and combine them in a graph. This way we will get delta G for one pair of ligands, for another pair. If we want to introduce redundancies, we'll introduce redundancies into those and basically cover the whole chemical space. So I understand it's a little bit abstract. I'll show a small example in a few minutes. Now the application of this is, we just very recently performed a large scan of almost 500 ligand modifications in a large set of systems following the cycle. So this one I was using also in the examples in the theoretical part. Before, we are interested now in the ligand binding. So we are trying to calculate the difference in binding of ligand 1 and its mutated modified variant ligand 2. But we are going in the alchemical branches, so modifying it in when it's bound to the protein and when it's free in solution. We probed many systems here, here's briefly the summary of all of these results. We have average and sign error. If we concentrate just on the average and sign error, and these are the PMX results. Again, the same trend holds as before. I'm showing now PMX results with amber force field, with charm force field, which did far worse, but combination of those does better than each of those individually. And you may wonder what's the first column. It's the so-called FEP plus approach, which is from a commercial software developed by Schrödinger. This is the software that is currently dominating the pharmaceutical market. The companies that are doing computational chemistry in the pharmacy business, they're using this proprietary software, which is closed source and is very expensive. But with open source, completely open source approaches, we are able to compete on par or outcompete this commercial software. I also have a breakdown by the system of those results, but we probably do not need to investigate those in depth. What I just wanted to say is the results, again, average and sign error, and just the bottom line. You don't need to go into each of these points, but it's the error can fluctuate. Depending on the system, we have very widespread, right? So the methods, they do give the average accuracy that is within 1 kilocalorie per mole. This is this golden threshold that is set somehow empirically or very arbitrarily, but it's frequently mentioned in the literature as well, that everyone is trying to reach 1 kilocalorie per mole error on average. And yes, it is 1 kilocalorie per mole on average, but it does depend very strongly on the system that you're looking at. It could be much worse or much better. Another interesting, I think this is one of the last examples here, the D3R challenge. We also participate. There are challenges that are brought to the community to predict binding free energies of ligands. And this is one of those where we participated. Unfortunately, we were too late to submit, so we participated after the fact, so we did not enter the actual competition. This is unfortunate. but I'll show the results anyways here. So how it works, D3R works as follows. Organizers ask pharmaceutical companies to measure some compounds in-house. They measure the activities and provide, in several stages, they provide also the crystal structures and provide the activities, but the users, the public doesn't know about those activities. And then all the groups just need to, around the world, they try to predict the binding affinity differences. And yeah, the best ones win. But yeah, let's go a little bit into, very little into the detail of the last year's challenge. So the challenge was to predict, one of the challenges was to predict binding free energy differences for a set of very similar ligands. So you see from the distance, you kind of see the differences. There are minor modifications only. It's called cathepsin S, this protein, and those are the inhibitors of cathepsin S, changing mainly several groups around the protein. And right, we joined our forces with another group who does modeling here, and provided us with a starting structure. So in the alchemical calculations, we're always relying on good starting structures. Only then our algorithms are expected to give some reasonable outcome. And yeah, this is exactly the approach that I was showing before. We first start with we have this library. So how do we explore this library? Well, we make a network of the edges in a graph, in a so-called graph. We make a set of connections between the compounds. And then we added redundancies. So to have, to be able to explore redundancies and to minimize the error of each prediction. All right, so now for each of these edges is a different individual calculation, which will give us a free energy difference. And due to the redundancies, we'll be able to reduce this error. And now can we calculate all that? This is just, again, the same schematic that I wanted to illustrate. We exactly use the same approaches. Here are just, we used some 109 edges or so. So that means 109 calculations we needed. And yeah, we calculated all of our data. And that's how the standard D3R challenge is evaluated. Root mean square error between all of these calculations and the experimental measurements is reported, and then we have different submissions. So the gray entries are submissions by other groups, and I plotted in our submissions. Well, we did not submit, so our participation among those submissions. So the smaller the number, the smaller the error, the better the performance, and we would have, had we submitted it on time, we would have outperformed all of the others. So it's very sad that we didn't submit on time, but nevertheless, it's interesting also to investigate now. Now, what do we see with different colors? Again, this is charm force field, this is GAF force field, this is amber force field, and this is our combined force field. Again, exactly the same trend holds. So consensus combined force field outperforms a single force field. And this is another way to look. It's not always we are the best. If we look, for example, at the trends, at the rankings, I must say that we could also be outcompeted by another group, which is also actually using thermodynamic integration. So it's always now, this year, the 3R challenge was really dominated, at least this part of the challenge, by the alchemical methods. Now, so we can also use the approach to, okay, so 2 minutes, approach to calculate absolute free energies. So we are always now talking about the relative, and by relative I mean we're calculating delta G, right? We have this thermodynamic cycle where we have free energy difference of wild type against the mutant, or the mutant against the wild type. But can we get the absolute free energy, where we would ask the question, hey, what's simply this delta G, right, of simply binding the ligand or unbinding the ligand? And yes, we can, but it will require some different treatments. It will require restraints. It will be larger. The perturbation is larger, so the convergence, or in other words, simulations need to be longer because convergence is slower. we need to also to modify the cycle. So now you see, we still rely on the cycle. I will not go into the details, but now it's clearly a much more involved calculation. But it is possible, and that's what we're working on now quite intensely. Just a small example that it really works. So my colleague Matea, he calculated a number of these absolute binding free energies. And the question, of course, is when would it be interesting to calculate absolute instead of relative? Well, it would be in those cases where we do not have a wild type and a mutant. It would be for those cases where we only have, let's say, 2 different proteins, or in this case, Matteo had more than 20 different proteins, and he wanted to know to which of these proteins the ligand binds best. So which proteins it could, for example, inhibit best, right? Then we really need the absolute binding free energy. And the results are as follows. They are not as good as for the relative free energy calculations because exactly of those reasons, slower convergence and larger perturbations that we have. But in principle, either with the Mateo's approach, where he used FEP approach, or with our non-equilibrium approach, we get very similar answers. With the, I think, average unsigned error is about 1.5 kilocalories, so slightly below this golden threshold of 1 kilocalorie, but it is, but the trends can be captured very accurately, anyways, also in the absolute free energy sense. All right, and with this, I will finish all the applications that I want to present. I wanted to acknowledge BioXL and that funds the free energy calculation project in Bert's lab, and also Gromox, which we are using for the calculations. And we have our own in-house PMX that we will get acquainted with in the tutorial session. Thanks all the people who also helped with this work. Thank you.
Thank you, Vitas, for the very clear lectures, interesting results, and also attracting, I would say, strategies to calculate ligand binding free energies. So I would expect some questions from the audience now.
Hello, thank you for the nice talk. It's not completely clear for me which is the difference between the equilibrium and non-equilibrium approach. It's only dependent on how fast we drag the system away from the initial starting point.
Yeah, that's a good point. Yes, there is a difference in the speed, but there are also different equilibrium approaches. So non-equilibrium that we presented that's the one way that I'm aware of, at least how to do it. We drag fast. Now equilibrium is again split into numerous approaches. One is where one drags very slowly. This is so-called slow growth thermodynamic integration, slow growth TI. This currently it's not anymore used widely because it requires the assumption of the system to be in the quasi-equilibrium state. So we drag as if so slowly that at every step we are exploring the full ensemble as if. But of course, there is a Hamiltonian lag, so to say. We're actually still dragging it. So this is the speed. The speed really matters. Another approach is not to do this dragging along the coordinate, but to distribute steps, to distribute lambda steps discretely. So we have lambda 0 and lambda 1, but we distribute them discretely. Some simulations will run at lambda equals 0.1, another 0.2, another, and so on. And they will run in equilibrium way. There is no dragging, but they're simply sampling those ensembles, obtaining equilibrium ensembles. And then the free energy between all the neighboring steps is evaluated with the free energy perturbation approach. So this is also, this is using free energy perturbation with the equilibrium sampling. Yeah.
Clear? Other question? Lady first.
Hi. I was just wondering, when we perform the classical MD simulation, so we include the all the bonded and non-bonded interactions. So in this method, when you are computing the free energy changes between like unfolded and folded state of a protein, or a protein in presence of a ligand and in absence of the ligand, so what are the, this gives us the free energy corresponding to all the interactions, or corresponding to a particular degrees of freedom, or a particular generalized coordinate?
Mm-hmm.
So
I think I understand the question. It will give, there is no generalized coordinate involved in the description of the free energy, right? It doesn't give us a profile along which, I imagine if you have a coordinate, you can get a profile along it. That's not how we applied at this point, right? We only get the two discrete, we only are concerned with two discrete states, and we get the free energy difference between these two discrete states. There is no, the only coordinate that we were involving is this alchemical coordinate. But we are not actually getting a profile along it. Well, we actually could get, with but it's not very, usually it's not very interesting, unless for the technical reasons to observe where the, I don't want to go there, but it's not so relevant. So you really get all the interactions that are perturbed, and so also bonded and non-bonded interactions are contributing to that.
okay, so it's free energy changes associated due to all the interactions because of the changes in the chemical coordinates, right?
Yes, if I got the question right, then
yeah.
yes.
And so there is there any contribution, like when a protein gets folded from the unfolded conformation, so it repels the water because of the hydrophobic collapse. So is there any contribution associated with the solvent? No.
Yes, absolutely yes.
Okay.
All these simulations are performed in a proper way. They are all solvated. Simply, we do not simulate the process of revealing the hydrophobic core to the solvent, right? That could be very difficult to converge, I agree, because we are not actually simulating the unfolding behavior. We're just simulating the folded protein with in two forms, right, where we do wild type and mutant, but it's always folded. And then we have another state, which is unfolded. That's more complex. We usually approximate that one, but that's just a technicality. This solvent interaction with let's say, the hydrophobic residue that needs to be mutated, or it is always there.
Thank you.
Mm-hmm.
If I may add, it depends on the difference between the two states, because when you perform this kind of perturbation from state A to state B, if you have major perturbation changes in the topology of your system with some additional waters that are interacting, of course, you need more time to converge. It's more complex, but just the difference between the two states, in principle, avoid the problem because you just don't sampling the path. So in that sense,
Thank you.
just to complete.
I have a question on the thermodynamic integration. So what if you have two states, and if one of the ligands, or if you just unsolvate a ligand that has charges, do you need to introduce ions that you wouldn't couple at the same time, or is there a procedure to do that?
Yeah, that's a very good point. And now, just to explain a little bit to everybody, to get everyone on the same page. So now the question is, if we have a charge change during the perturbation, right? So one ligand is uncharged, another is charged, or one amino acid is alanine, another is aspartate in its unprotonated form. So we would be changing the overall charge of the system and in the simulations. So first of all, it would be more difficult to converge because one needs to also accommodate change by changing. By this change, one also needs to change the solvation shell or arrangement of the solvent around this residue. But that's just a sampling issue, because with longer sampling, this would be taken into account. Another issue with the simulations is that the use of the long-range interaction treatment, which usually now It is particle mesh Ewald summation, so which it does not, strictly speaking, does not like this uncharged, uncompensated charges in the box, because it would smear the background charge over the whole box. But now, so people historically tried different approaches. They tried, exactly as you mentioned, introducing an ion. So if we are interested in going from neutral box to a charged ligand, they would at the same time introduce an ion of the opposite charge, and this way the box would remain neutral. I advocate a different approach. I advocate putting both legs of the thermodynamic cycle into the same simulation box. So we are interested in ligand bound to the protein, neutral ligand, and another another state is charged ligand bound to the protein. However, we have to remember that we're only the delta G will be meaningful. There is another leg of the cycle where we have neutral ligand in water and neutral and charged ligand in water. So if we put both of these legs of the cycle into the same box, so both of these states in the same box, just reverse, and we couple neutral ligand bound to the protein and charged ligand in water, and we perturb all of this into the charged ligand bound to protein and neutral ligand in water. We get both legs of the cycle at the same time. The charge of the box is conserved, and the answer that you get from the thermodynamic integration or whatever method you're using is automatically delta G.
Yeah, the issue is about, as you said, about the convergence. When you have the passing from charge to neutral, of course, you need convergence, particularly when you switch off the electrostatic contribution. That could be an issue, but yes,
yeah,
there are also some recent, yeah, please.
Yeah, but that's the sampling issue. So one.
Yeah, right. Yeah, right. There are also there's a recent paper that deals with this problem about using free energy perturbation in charged ligands, and there are suggest some solutions. So it's quite a hot topic in that field. Other question?
What do you mean by mixing force fields? What do you mean by mixing the force fields? Thank you.
Yeah, I didn't explain that in detail, but mixing in this case is not mixing the functional form and not mixing the parameters. It's really combining the already calculated and processed results. So really combining just the free energy differences. If you get free energy difference calculated from amber, well, number 1, and you get a number from charm, number 2, it is likely, and in all of these cases that I was showing, the mean of those two numbers will be closer to experiment than amber alone and charm alone. It seems that simply there is these combined results that the force fields like to point in the opposite directions from the experiment.
So what's consensus? So you take the mean, right? But you said consensus.
So the question was what is the consensus approach in these force fields? And consensus, we probed various consensus approaches. We probed machine learning, so basically what is the most optimal ratio? Maybe we need 20% of amber and 80% of charm or so.
So that involves more than one system.
Yeah, so these were our early approaches where we probed, but in the end we saw that simple averaging, so because we only have 2 force fields, that we usually run the simulations now in 2 force fields, we don't use all the zoo, right? This becomes computationally expensive. So our consensus now is only using an average of the 2 latest versions of amber and charm.
Thank you.
Okay, so now it's lunchtime. So thank you again, Vitas, for the nice presentation. Very nice, clear lecture. Thank you all for this morning and to speakers. Now it's lunchtime, and we'll be back at 2 p.m. in the computer room, so 156 in the main building, as you know. See you later.